All right, so welcome class. Today I'm going to be talking about a few different questions that I got online. So first let me share the link. All right. So I'm going to walk through a few different questions, and then I'll just start walking through the stuff in the project as well. All right, so I got a few really nice questions from the red group, which is I think Paige's group. I was the one who sent it to me, so thanks very much for that. I really appreciate it. So we have a few. So the first question is, can you elaborate on how stacks and continuations are the same? So I'm going to kind of try to show that by example. So, okay, let's say we have a function like f of x, and then we'll call plus g of x, h of x, and then let's define g of x will be plus x1, and then define h of x will be plus x2, and then let's just make sure this code works. Ooh, that's not good. $190. Okay, I'm going to take this out and just put to do here so we can fix that bug for a second. And then I'm going to split my screen the other way. Okay, good. Okay, so let's say that I make a call to f of 20. I get back 43. So what happens when I call f of 20? Well, I'm going to get this call to f right here is going to be passed into this function f, and then x gets the value 20. And then I'm going to start evaluating this call to plus. So how do I evaluate the call to plus? Well, I have to do two things. Racket's interpreter is going to execute. It's going to go through all three of plus, evaluates that, evaluates g of x, and it evaluates h of x. All right? So to evaluate plus, that's pretty easy. That's just an atomic thing that's included in the Racket top level. What about the call to g of x? Well, the first thing to ask ourselves is g of x a tail call, or is it a direct style call? And the crucial thing to remember is that when you call g of x, if there's anything that has to be done before g of x after g of x returns and before f of x returns, then it can't be a tail call, right? So to phrase that a little bit more correctly, or just understandably, when I call g of x, after I call g of x, what do I have to do? Well, I have to store the value that g of x returned, and then I have to remember to keep going on and computing h of x, and then after I'm done computing h of x, I have to remember that plus call right here. And then I actually have to perform the application. So what I'm going to do is I'm going to walk through each of plus g of x and h of x to compute the values passed into plus. All right, and while I'm computing g of x, I need to throw something on the stack to remember what to do after I return from g of x. All right, so the stack is used for return values and handling return values. Because right when I'm executing g of x, the computer stack remembers to go back and execute h of x, and then continue to perform the application of plus. All right, so how can I codify that? Or how can I see that that's related to a continuation, right? Basically, what does any of this have to do with continuations? Well, it's pretty easy to do that. All I'm going to do is I'm going to do call cc lambda k, and then I'm going to bind this continuation right here. And then let's just pass k as an argument to each of g and h. So I'm going to add k as an extra argument right here. All right. So what's going to happen with this call cc right here is that it's going to bind the current stack at this point in time and pass it to this function g right here. All right, so what happens if right here I call k of 23, or let's say 500. I use the number 23 a lot in examples, so I should use something else. Okay, well, let's see what's going to happen. And by the way, when you see a top-level define that has multiple statements after it, then you'll sort of know that each of these gets executed one after the other. That's how that works in Racket, if you haven't picked that up by now. So there's also a block in Racket called begin, which just takes a series of operations and sequences all of them. You could equally well use a call to begin right here. That would also work. All right? So they're the same thing. All right. So let's see what happens when I call f of 23 right now. I get back the number 500. All right, and why is that? Well, it's because I can think of call cc as taking sort of a snapshot of the stack right here. Now, if I look at this and I think, well, what is the stack at this point? I have to think to myself, okay, well, after I return from, or no, let's ask it better. If I were to return at this precise point, what would the value be? All right, so how can I find the stack, or how can I find what k will be bound to? Well, it's going to be bound to something that's essentially like this. Because if I were to take the call cc out and just replace it with the argument passed into the continuation k right here, then I would get what the stack is. All right, so that's the way in which continuations basically turn the computer stack into a function that you can execute. Right? When I invoke this continuation k right here, control is going to jump back up to the point where the call cc was taken. And then that's going to get replaced with the answer, whatever was bound into k. All right, now let's look back at our interpreter, our interp-cek interpreter. let's see, is there another question from this group? I think there is. Yeah, there is. There's one that I can quickly answer. So the next question is, does a trace call indicate whether or not a call is direct or tail recursive? Well, this one is pretty easy. We can answer this right off the bat. Actually, you know, I guess it's actually more nuanced than I thought at first. So let's play around with this. Let's do example factorial. I have to change the name. So let's do fac direct. Yeah, sorry, I keep changing the name. I'm going to do, does trace inform you whether it's tail or direct? So the answer is kind of no, but also sort of yes, and I'll sort of show why. So it doesn't immediately mark whether it's tail or direct recursive with something like a T or a D or anything like that. There's no way to know that, although some compilers do expose that information for you. So for example, I used to do a lot of programming in a language called Objective-Camel or OCaml, and that language was really focused on speed. Racket is not a functional programming language that is so much focused on speed. In fact, Racket, especially because it lacks a really precise type system, has a whole lot of runtime checks that makes it rather slow to execute, in fact. All right, so this language Objective-Caml that I programmed in, it was actually pretty crucial. You know, if you were trying to make it really fast, you really wanted to ensure that various calls were actually tail calls. And the compiler will actually give you some debugging information about whether certain things are tail calls or not. All right, so in that case, it would actually tell you, and probably there is something similar if you dug deep enough into Racket, but I don't think it's something that is exposed easily so that students would be able to find it, unfortunately. So let's just see and look at this call to trace and see whether we can find this. All right. Okay, so now we're going to make a tail recursive version called ACK. Let's just replace this with times. We'll do this with fac tail n-1, and then times ACK n, and then we'll trace both of them. Okay, and now let's do fac tail. No, let's do fac direct first on 5. Oh, shoot. Here I'm calling factorial. I want fac direct. Okay, so here we can see every time you see a right arrow, you're seeing something being pushed onto the stack. And every time you see a left arrow, you're seeing a sort of a return. All right, so we can see that fac direct is building up stack frames because it's pushing up calls to fac direct on itself. All right. Now, what if we have fac tail? Let's do 5, and then our initial accumulator will be 1. Well, here we can see, just by observing the fact that the stack never grows, we can see that it must be a tail call. All right, so we're hopping from here without extending the stack, We keep going up, and we eventually return. All right, so in some ways, even though even though the trace functionality doesn't tell you precisely, sorry, the gain is set too high. Even though that doesn't tell you precisely whether the function is tail recursive or not, in the sense that it's not explicit about it, it is fairly helpful if you have a function that you suspect might be tail recursive. Well, if you trace it, you can find out whether you are indeed correct. All right? So that's a good question as well. All right, let's see if we have any other questions. Yeah, let's see. I think there are some other questions I have from the red group. Okay, so let's see. Can you benefit on using let call CC as a loop over a more traditional recursive loop? Well, that's a really good question, actually. So we have this idiom. So let's do something like define, let's write some function foo x, and this is going to be a recursive function. Let's do something like, actually, no, let's do ors. No, let's write a function called or that takes in a whole bunch of thunks. And the idea is that we're going to pass or. We can pass or something like we're going to pass or something like lambda true, or no, let's do lambda false, lambda no arguments true, lambda no arguments, and then the omega term. So that's going to be the omega term right there. Okay, let's do, and then we'll make this a lambda L, take a list of arguments. So this is actually showing sort of two examples in one. So L is an argument list. And the question is, why might we want to have call CC? And I'm going to show you sort of a way we could do it, or at least show you one example of why we might want it. So let's write ourselves a helper function here. Define helper, which is going to take a list of expressions, or thunks, that we're going to execute one by one. And that's going to be match thunks, and we're going to say it's a list, so if it's an empty list, return false. Because if I pass or nothing, then the result should be false. It shouldn't be true, right? Just like I would have in Racket. What about if I have or of head and tail? Well, then I can do something like, I might say something like, let's do define, and this is going to be kind of an artificial example because there is a better way I could do this, and I'll show you precisely what that is in a second. But let's say I did it this way, which is a little bit artificial, I admit, but it's a good example of why you might want to do this kind of call CC thing, which is basically being able to jump to the top level of somewhere you took a continuation initially. So let's do something like define, let's do define first as apply head, and then we're going to define rest as helper on TL, and then I'm going to do or of first and rest, and let's see if I can make this work. I probably need to have an extra case to handle a single element list. Here I'm just going to return, I'm just going to call HD, which is going to be a function. And then I'm going to call helper on L. And that needs to be a quasi-quote. Okay, and then I'm going to call or. Ooh. Here we go. Let's call it my or. Yeah, there we go. All right. And note that I want to use brackets or right here rather than my or. Yeah. Okay, so I think that will work. Oh. Okay, let's check it out, see if it works. And it doesn't work. It doesn't terminate because okay. And it doesn't terminate because eventually this omega thing gets forced right here. All right, so because I call later, this is going to be a problem. So what are the options? Well, there are a few options. The first is I could do option 1, which is the most obvious option, is that I could just write, I could just define this whole thing as or of first, and then if not, helper TL. All right, and that would use brackets or to short circuit this behavior. All right, so let's prove to ourselves that that one works. So this is probably the correct answer. I'm going to show you a way that you could use call CC to do this. It wouldn't be very idiomatic, and I think it's a good example of why you probably shouldn't be using call CC a lot. But it's a good example of why you can. And there are other situations in which you might end up in this boat later. Okay, so this one returns true. Okay, so how could I use call CC to do this? Option 2, using call CC, is that let's say that I'm deeply in so call CC is really good for the kind of thing where I'm like deeply embedded in a recursive call, a few stack frames deep, and if I keep going, I'm going to run the I'm basically going to run sort of out of, I'm going to keep running when I don't really want to. I want to basically jump back to the beginning of the place where I took that continuation. So call CC is really good for that. So let's do call CC of lambda k. right? Now, note, whenever I invoke k, so let's define first HD. If first is true, then I'm just going to invoke k and return true. Otherwise, if first is not true, I'm going to call helper on TL. And then here, I'm going to invoke, I'll invoke k on f. I actually don't even have to do this because I could just return normally. I could also invoke k on head right here. Now I can call, here we go. Now if we try my or, ooh, that's not good. Let's do some debugging on this. My or on lambda true. Huh, that's weird. You know what the problem is? Is that, and this is pretty nuanced, it's that I put the call CC outside of the lambda. I need to put it inside of the lambda. And the reason is basically that when I put call CC outside of the lambda, right here, my or is just binding a definition. It's not really binding a function, right? This is a nuance and kind of a complication of the keyword define. It's used to define both variables and also functions. All right, so because it can be used for both, it makes it a little bit tricky if I do this style where I do define f of f to be lambda x and then something right here. All right, so that's the trick that I was running into. If you'd like to understand more, I'm happy to elaborate and explain kind of in person. Ooh. I think I'm messing up the syntax here. Here we go. That's the problem. I also need to move this call to helper. Okay, and now it works. All right, good. Okay, so the basic answer to that question is I can use call CC to sort of jump out of a deeply nested recursive call. And I want to show you another example of that, and it's actually in the solution to the E5 starter code. Not E5 starter code, just the E5 code. So if you remember the definition of capture avoiding substitution, let me copy this back into Day's work. So here's another use case for call CC. And let's copy over my FreeVars implementation as well. This is something I think really really nicely illustrates what call CC is and why you could use it. So let's do capture avoiding substitution. Let's do capture avoiding substitution of lambda xx. We're going to replace x with y. Oops. Forgot to quote these last two. Okay, and that works. Let's see. Here we go. So this is the example that won't work. Right, so we can't replace y inside of this lambda because we've got a lambda y. So so if we tried to replace this x, with y, it would get captured by this binder right here. Right, so we couldn't do that. And so capture avoiding substitution is telling us we failed at that. Let's try something like this. Let's do lambda z, lambda y, x. We're still going to get failed. All right. How about, and I'm going to show that this is because I'm writing this with capture avoiding with call CC. So let's try bad capt avoid subst right here. And then let's just do all of this, which is what I think probably most people wrote for the solution, because I didn't really talk about this nuance when we were originally writing the solution. So we're going to try to write capture avoiding substitution, E0, replace x with E1. Right, so that's what we're going to try to do. But we're going to find out that it just doesn't work sometimes when we're deeply embedded in some term. So let's say that right here I return failed. All right. Well, I'm going to try to run this. And see what I get is that I get this lambda z failed thing. And the reason why is because the first lambda works out because I'm trying to do this lambda z. So lambda z is not equal to y, which is the thing that I'm replacing. And so I end up doing this thing where I hit this case right here. And then I perform t inside of e body. But then if I just drop failed right here, it's going to mean that I reconstruct this lambda y term and then do this failed thing right here when really I want to pop failed up to the top level. All right, so I can use call CC to avoid that, because really what I want to have happen is that if I want to return this tick failed thing, I really want it to be returned to the beginning of the call of capture avoid substitution. I don't want to have to return this failed term deeply down inside the embedded term. Okay, so this is another use case for call CC. Bad capt avoid subst inserts failed deeply into the reconstructed term. But using call CC avoids this and the fixed capped avoid subst passes. All right, so that's basically an answer to when would you want to use call CC deeply embedded in some term? All right, and what use could it be? All right, so let's see. I think that's pretty much the last question I want to recall today. Yeah, I think that's probably good for today. But I'll probably start office hours tomorrow, and that's my plan.